The main concepts of exterior calculus. Number 1. Differential forms. Objects that live in the exterior algebra of a manifold. A differential form can be thought of as a generalization of a function, a zero form, a vector, a one form, and so on, etc. So a zero form is just a scalar function, f of x or f of xy or f of xyz, etc. And a one form is the differential of a function, often written as omega equals, a dx plus b dy plus c dz in R3, where a, b, and c are functions of the coordinates and dx, dy, dz are the differentials of the coordinates. Now, a two-form might look something like this. Omega is equal to p dx wedge dy, q dy d wedge dz, plus r dz wedge dx. The wedge products encoding geometric signed area elements, and p, q, and r are functions. So we use the general omega notation for any type of differential k-form. Now, the exterior derivative operator, lowercase d, is an operator that acts on differential forms, and it does so to create a new differential form. It generalizes the idea of the differential of a function and the gradient, divergence, and curl operations in vector calculus. For a zero form, a function, the exterior derivative is just the gradient, it is the differential df involving the gradient. And it's defined here. So in this case, it produces a one form, which is a covector field. And if del f is the gradient, df is equal to del f dot dx, where dx is a set of differentials. So it is a dot product that produces a scalar. For a one form, the exterior derivative is analogous to the curl of a vector field. And then a two form is akin to the divergence of a curl, related to flux and volume integrals. The wedge or exterior product, as we defined in our first video, remains central to exterior calculus, and it is used to combine forms. The wedge of two one forms, for example, let's take the two one forms omega and eta here, and wedge them together. There is a distributive property that takes place, and wedging the differential forms in a particular order does matter here. Recall that dy wedge dy is 0, so we get here a two form, which is encoding an oriented area. Stokes' theorem from vector calculus is a powerful result in exterior calculus because it generalizes the classical theorems of Green, Gauss, and of course Stokes from vector calculus to differential forms. And differential forms are stronger arguments because it relates the integral of a differential form over a boundary to the integral of its exterior derivatives over a region enclosed by a specific boundary. And it is usually denoted here, with the curly dm denoting the boundary and m denoting the space enclosed by the boundary. So the integral over the boundary of a differential form is equal to the integral over its surface of the differential of that differential form. So a little more on differential forms. So let's consider the differential forms in R3. Suppose we are working in R3 and we want to analyze a vector field using exterior calculus. What does the expression for our vector field look like? One might define the vector field F using the basis vectors I, j, and k as follows. But we can express this as a differential one form, omega equals p dx plus q dy plus r dz. Taking this vector field, the exterior derivative of this one form, which can be thought of as the curl of the vector field, is given by the 2 form here. And you can see the connection in the coefficients here of the different wedge products hinting towards this idea of the curl of the vector field, encoding the rotation or circulation of that vector field. Now, integrating a 2 form over a surface, consider omega, the 2 form given here. Let's say we wish to integrate this 2 form over a surface M in R3. To do this, we need to parametrize the surface M and compute what is called the pullback of the 2 form to the surface. The pullback of the 2 form represents the oriented area element on the surface, and the integral gives the total area. So, for example, if the surface M is a unit square in the xy plane, then the integral becomes the integral over the manifold M of the differential form, given here by the wedge product dx wedge dy, which is integrated over the boundary of the surface, del m, dm, curly dm, which is just the boundaries of our unit square. So a differential K-form is a covariant antisymmetric tensor field of rank or degree K. And the exterior derivative of a K-form is an operation that produces a K plus 1 form. It lifts up the K form into a K plus 1 form. The sum or difference of 2 K forms is just another K form, and the product of a K form with a function, a 0 form, is just another K form as well, a scalar product. So now, the exterior wedge product, or sometimes called the exterior differential product, the wedge product, of a K form, and let's say a Q form, is the mapping wedge, and it takes the product of 2 elements and produces something in the wedge space K plus Q dimension. So for instance, 1 forms alpha 1 and alpha 2 wedged together, antisymmetric form, is a mechanism for constructing 2 forms from 1 forms. So again, what we're doing is we're taking a K form and a Q form and producing a K plus Q form. So in general, the wedge product of a K form, which is an element of wedge K, and a Q form, which is an element of wedge Q, produces a K plus Q form, such that if you swap the particular elements, you retain a negative sign up to a certain degree. The larger vector space, consisting of all the direct sums of these vector spaces, has a dimension given here to be 2 to the n. And this space together with the exterior wedge product is called the Cartan or Cartan exterior algebra of the cotangent space and is the Grassmann algebra of differential forms. So this exterior derivative operation maps a k form to a k plus 1 form, such that for any k form omega, say omega 1 in wedge k and omega 2 in wedge q, we have the following that are satisfied for the exterior derivative. So the sum of two k forms, or a k form and a q form, the wedge of a k form and a q form, and that last one, d omega equals 0, becomes an important part of closure for something later we will define as a complex. Let f and g be two functions, two zero forms, and let alpha and beta be two one forms. Then the following properties are valid for the exterior derivative. df is the ordinary total differential of f. The exterior derivative of the product of two functions follows the exterior derivative of a function and a one form follows here, and the exterior derivative of the wedge of two one forms also follows here. If the derivative of a k form phi equals 0, then phi is said to be closed, and if the form phi equals the exterior derivative of an omega, then phi is said to be exact. So familiar exterior differential forms in R3 with the Cartesian coordinates are integrands of the following form. So let's say we have the integral of alpha, which is a line integral, then it has the differential 1 form as its integrand here. If we're talking about a surface integral with the integrand beta, beta expands in the following way, which we can expand in terms of the wedge product of these differential forms here. That's a 2 form. And for a volume integral, the integral of gamma, the volume integral, can be expanded here. And because in R3 a volume integral would be a top form, then we have a more simplified version of that integral for the 3 form. The Hodge-Star operator takes k forms to, in the case of R3, 3 minus k forms. So for example, we have the following relations for the Hodge-Star operator, which can be used in front or as like an exponent when written. And it relates to the wedge product because it is an isomorphism between these forms. Here we can transform between a 0 and a 3 form using the Hodge-Star operator. And we can also move between the dimensions of 1 and 2 forms, again using the Hodge-Star operator. So this one-to-one isomorphism allows us to create what is a duality, which is central to Stokes' theorem. We observe that the wedge product of a 1 form and a 2 form corresponds to the dot product. For example, alpha wedge star beta corresponds to the dot product of two vectors a and b. The exterior derivative of a 0 form is the total differential, df. And again, that's given by the gradient del f times the differential vector dx. The exterior derivative of a one-form alpha is d alpha, and this relates to the curl of a vector field. And that is because the wedge product involves the cross product. The exterior derivative of a 2 form, represented by beta here, reduces to d beta is equal to the following, which corresponds to the divergence of the vector field V times the element of volume. We can summarize all of these results in the following way. For 0 forms, for 1 forms, for 2 forms, and for 3 forms, or top forms. For a top form, the curl of a gradient is equal to 0. Excuse me, for a 1 form. The generalized Stokes theorem. Let M be a compact, oriented, smooth, K-manifold with a boundary dm. Let phi be a K-1 form M on M. Then we have the integral over the surface M of d phi is equal to the integral around the boundary of phi, where phi again is a K-1 form and d phi is a K form. If K equals 1, M is a one-dimensional connected manifold. If M is contained in R1, then M is just the interval from A to B, and the boundary dm has dimension 0, so it is just the pair of points A and B. So for a function f of x, which is a 0 form on the interval from A to B, the total differential df, which is given by df dx times dx, or f prime dx, reduces to the fundamental theorem of calculus. But this doesn't naturally extend to higher dimensions without differential forms. Constructing the bigger picture. In the context of differential forms, we have 2 new operators to talk about: the sharp operator and the flat operator, sometimes referred to as musical operators, for obvious reasons. They are maps that relate covectors or one-forms and vectors or tangent vectors, providing a way to translate between the dual space of vectors and covectors. These operators play a very significant role in differential geometry, and they are essential when working with the metric structure of the manifold, because the sharp and the flat operators are directly related to the metric tensor and the inverse metric tensor. Now, a flat operator takes a vector field, which is something pointy, or a tangent vector, and maps it to a one form or covector, which is essentially flattening this pointy vector. It's giving us a real number in order to measure it. So if we let V be a vector field, V flat is a one form associated with V. In other words, in the world of tensors, this operator lowers the index of a vector field, turning it into a one form via the metric tensor. So if the flat operator is related to the metric tensor on the manifold, it provides a means for identifying tangent vectors with one forms via this metric. So if V is a vector field, G is the metric, the inner product on the manifold, then the flat operator is defined as the inner product of V with something else producing a particular metric. Via the inner product, of course. In R3, with a standard Euclidean metric, a vector can be expressed in the following way, with partial derivatives as the basis. V flat will have the differential basis given here, which is a covector field. The sharp operator is the inverse of the flat operator, therefore taking a one form and mapping it to a vector field, or a tangent vector. And if omega is a one form, omega sharp produces a vector field corresponding to omega when paired with the metric G. Now, if we're raising the index of a one form, turning it into a vector field, we will do this via the inverse metric. Therefore, the sharp operator is related to the inverse metric. And so we see that the sharp and the flat operators are inverses of each other. Let omega be given by dx plus dy plus dz, a one form in R3. The sharp operator gives us this vector field. So the flat operator takes a vector, turns it into a one form, lowering the index. The sharp operator takes the one form, turns it into a vector by raising the index. And it is crucial in working with the duality between vectors and one forms, or contra and covariant tensors. We make an important note. In the absence of a metric, these operators don't exist in the same way. The metric is needed to relate the vector space and its dual. In a Riemannian manifold, the sharp and flat operators, well, they're used extensively to define geometric structures such as connection, or to express the covariant derivative. The exterior derivative of f is just the flat operation on the gradient del f. So df is a way of measuring the gradient field. Consider we're measuring temperature in a room. On the left it's cold and on the right it's hot. One can see the temperature variation through color as a scalar field. If we were to trace out the level set curves which are oriented in a particular direction, this would be a covector field on our scalar field. And if we want to relate this to the gradient of this scalar field and overlay it with the covector field, we get this picture. And so the covector field is measuring the vector field placed on this scalar field. It's important if we visually map out some of our observations here. So the exterior derivative of 0 is 0. And in R3, we can map anything from the null space into the set of scalar functions of 0 forms wedge 0. Now if we let f be an element of wedge 0, we can take an exterior derivative and create a 1 form which is in wedge 1, which is df. If we now let alpha be df, we can take the exterior derivative and make a 2 form, dx wedge dy. And if we let beta be that new wedge form, then we can take the exterior derivative and move it into a 3 form with the exterior derivative operation. Since R3 is our dimension is 3 here, a 3 form is a top form. And that means that the second exterior derivative of beta will result in 0. So this exterior derivative forms a closed chain, a chain which we can refer to as a complex. Starting with the null space up to the 0 forms, then up to the 1 forms, over to the 2 forms, back to the 3 forms, and back down to the null space. This is known as the de Rham complex, and it has something to do with what's known as the de Rham cohomology group. And we can fit our Hodge star operations here in blue and our sharp and flat operations here coming off the set of 1 forms. De Rham cohomology is an element of topology that helps us define the global structure of a manifold. And we can rewrite all of our familiar vector calculus operators, such as the divergence, curl, gradient, and the Laplacian, in terms of this new map, where we use the Hodge star operator and the flat and sharp operator along with the exterior derivative to form these new products in our new space. The exterior derivative extinguishes the need for a coordinate system. Let's explore the gradient for a moment. The gradient is found by taking the derivative of f and sharpening it. And when I say derivative, I mean the exterior derivative. So it's a set of mappings along our chain here, from wedge 0 to wedge 1, sharpened to the vector space V. For the divergence, we start with a vector field, and we're going to use the Hodge star operator along with the differential operator and the flat operator to create a chain which gives us the divergence. Okay, so noting where each element of our composition would fall, we can map it out here. From vector field V, we flatten to the 1 form, Hodge star to 2, derivative to 3, Hodge star to 0, which is a scalar function. The divergence gives us a scalar value. And that's in the same way that the gradient gives us a vector field. The curl of some vector field capital F can be found with this mapping in our complex. So the vector field is flattened into a 1 form. We use the derivative to a 2 form, a Hodge star back to a 1 form, and sharpen it to a vector field. The Laplacian is found by starting at a 1 form, a 0 form to a 1 form, 2 to 3 back to a 0 form, with alternating with the exterior derivative and the Hodge star operator. Differential forms provide a stronger framework for derivatives in higher dimensions. And the Hodge star operator? Well, it's like our secret key that unlocks new ways of thinking about geometry and calculus in higher dimensions. It provides us with a mapping between dimensions, k-forms, and n-k forms, in n-dimensional space. And a k-form just represents an object that can be integrated over a k-dimensional surface, like a curve, or a surface, or a volume form. The Hodge-Star operator transforms a k-form into an n-k form, and again, this represents an object that can be integrated over a complementary n-k dimensional surface. Something that happens in one space has a corresponding action in the other. Thus, this transformation allows us to translate information of one kind of object like a vector field, or an area, into some other kind of object, like a volume or a flux. And this framework is exactly what Maxwell needed to describe his equations of electromagnetism. So in three-dimensional space, if you have a 2 form representing something like a surface integral of a field, the Hodge-Star operator transforms it into a 1 form, which can be interpreted as something that's related to flux. Thus, it provides essential mechanisms to rotate your understanding of geometric objects across dimensions. So next time, we'll explore how this allows us to understand what Stokes' theorem is saying, and then perhaps we'll explore a little electromagnetism. Until then, thanks for watching. I hope you liked this video. Stay tuned for the next one, and please hit that like, subscribe, and notification bell for more videos.